Hello everyone, welcome to our presentation of reverse engineering of the brain. Today we're going to emphasize on the topic of prosthetic hand. Now let's get into the presentation.
Reverse engineering the brain is one of the grand engineering challenges consisting of constructive models built for implementation, analysis, and design recovery. By reverse engineering, we're able to model the framework of the brain through machine learning that enables us to learn complex behaviors and create artificial psyche. In our presentation, we elaborate the theme of artificial hands, our myoelectric hands to be precise, a direct emerging technology that contributes to the challenge. It combines a multitude of sections of reverse engineering and neuroscience. The technology will not only help the disabled people, but also it contribute to the medical science to introduce further innovation and improvement. So in this report, we are emphasizing the state purpose. The demonstration of machine learning on par with human intelligence and perception is still elusive to date. The history goes far back to Bellman's optimality principle that tackles the task complexity, balancing the work done by dissipating a significant amount of computing supplies. During the early 16th century, Dr. Ambrose Paire chalked on the idea of prosthetic limbs. In 1980, IBM mathematician Benoit Mandelbrot unlocked the miraculous depth of complexity that equally brought a new phenomena for the neuroscientists to understand about the emergent properties. He plotted the variable points on a plane, colored the outcome, and that emerged into infinite scepters and spirals, and this distinct pattern of neural connection introduced artificial intelligence. The University of Michigan researchers have been working to address new approaches to myoelectric limbs that centers on regenerative peripheral nerve interface, which not only allows healthy growth of nerves but also amplifies the neural signals from brain to recordable muscle indicators guaranteed to stay for years.
Moving on to the problem statement, which is more about designing a prosthetic arm that replaces the function of an existing limb. Having that said, this prosthetic arm needs to meet the requirements of stakeholders to be electrically powered, cable sensing controlled, connected to batteries and motors, has a greater grip mechanism along with high sensation feedback as shown in figure 3 on the right hand side. Having that said, this prosthetic arm consists of major components such as socket, suspension, control cable system, and terminal device, which will be discussed about later in the slide.
How does our brain have the ability to control the movements of our body parts? The voice inside your head, your consciousness, the way we can all show emotions. How does our brain have the ability to do all this? This is all done through the reverse engineering of the brain. That meaning that the brain is taken apart into its individual components, such as neurons or nerve cells, to analyze how a person thinks, how we remember things, and how we act. A prosthetic hand is similar to a robotic arm that records brain signals from the motor cortex of the brain and interprets these signals as movements on the prosthetic hand. You might be wondering as to how these signals are transmitted from the cortex to the hand. Well, a tiny chip that could fit on your fingertip is installed just above your skull, and electrodes are placed on the surface of your brain, which allows the prosthetic hand to be wireless and allows it to move however you want it to.
So why is it difficult to produce a prosthetic hand? So most prostheses that we think of today are composed of three separate parts. Most important part is that they contain a custom fitted socket that attaches to the lost limb, which typically connects to a body or an internal structure. The prosthetic body then connects to an object either used for stability such as foot or any other object that performs a specific action if used in the upper part of the body like hands, arms, or fingers. So the socket that connects to the limb is usually composed of plastic, often a soft silicone rubber, to maximize the fit while trying to provide the most comfort. This material is not in itself extremely expensive, but these components are often expensive to manufacture and to create. After all, they need to be customized for optimal fit and comfort to each individual. Otherwise, the prosthetic can cause pain and also will work incorrectly. So now the question arises, where are we on our research? So a research team led by Dr. Paul D. Marasco of the Cleveland Clinic set out to engineer human perception with robotic technology. So 2 women and 4 men are currently taking part in that study where the ages between 28 to 68. Each was missing an arm from above of their elbow. Previously, they had undergone a procedure known as targeted reinnervation. For this procedure, a surgeon redirects the nerves for the missing part of the limb to the remaining muscle. When the muscle contracts, those signals can be used to drive the motion of the bionic hands. So the team of neuroscientists and the engineers built an interface between the brain and the prosthetic hand to create illusions of the motions of a hand, forming complex gestures such as grasping an object. So the algorithm directs to vibrate the re-innervated muscles in the arm. These vibrations caused perceptual illusions that tricked the brain into thinking that hand was moving in complex ways. So even without seeing the prosthetic hand, the people who took part in the study could rely on this illusionary feedback technology to position their hands effectively and correct for their own errors, and also can get a better sense of natural movement and control with their bionic prosthetic hands.
As a prosthetic hand cannot be compared to a real organic hand, it comes with many complications. As with any machinery, our focus as engineers with prosthetic hands is also safety. But it doesn't come with the universal fit, and it also doesn't come with various functions, such as for rock climbing, you would need a specific prosthetic just for that occasion. These are all the complications that engineers of today face, and they have not yet found a solution to. So recreating a part of your human body is no simple task, and the engineers of today lack the proper knowledge of human anatomy to try and replicate the prosthetic hand.
At the end of the day, the grand engineering challenge of reverse engineering of the brain may seem really tough and hard task to do, but it's also true that our centuries of hard work has led us so far that we have already started producing and using prosthetic limbs, especially in the past few years, where artificial intelligence, high algorithmic and statistical knowledge have become the major fields for technologies, even though they refer to different fields, but they all are interconnected and work together to make a proper and concise prosthetic arm that will help society, which overall shows how engineering creates solutions serving the welfare of humanity and needs of the society.
Here are all the references that we have used on our presentation. Thank you so much for watching.